Today, we're talking about a huge breakthrough from Google called TurboQuant. This is a brand new algorithm that's tackling one of the biggest, most expensive problems in AI right now. And what's really cool is, it's not doing it with bigger, faster chips, but with some incredibly clever math. So how does it all work? Well, it starts with a problem that you've probably felt yourself.
You know that feeling, right? You're deep into a really complex chat with an AI, things are going great, and then it just starts to lag. You're waiting longer and longer for every single new word. Well, that frustrating little pause, that isn't just you. It's actually a symptom of a massive memory problem happening under the hood of pretty much every large language model out there today. So at the heart of this problem is a specific component called the key value cache, or just KV cache for short. And as our AI conversations get longer and the models themselves get more powerful, this cache has become the single biggest bottleneck holding back AI performance. The easiest way to think about the KV cache is as the AI's short-term memory. See, to understand what you're saying now, the model has to remember everything you've already said. Instead of rereading the entire chat history for every single new word it generates, which would be incredibly slow, it stores all the key points in this cache. It's a super smart shortcut. But, and this is a big but, it has one massive flaw. And that flaw? It's all about its size. It just grows and grows in this frighteningly predictable way. Every new word you type makes the cache bigger. Every extra person chatting with the AI makes the total cache size bigger. And of course, as the models get more powerful, their caches get even bigger. It's this linear explosion. The more you use the AI, the more memory it just devours, until it slams into a wall. And look, we're not talking about a minor inconvenience here. As this quote spells out, this memory wall is now the central challenge. In systems with high demand, this cache can balloon to terabytes in size, and that can easily overwhelm even the most powerful GPUs. It's what limits how many people can use an AI at once and just how long and complex our conversations can really get. So you've got this massive data problem. What's the first thing you think of? Well, for the AI community, the answer seemed pretty obvious. If the data is just too big, why not just shrink it? This process is called quantization. Basically, quantization is all about representing the exact same information, but with less data. You take a high-precision number, like say a 16-bit number, and you figure out a clever way to represent it with just 4 bits, or maybe even 3 bits. It's a pretty standard compression technique, and on the surface, it seems like the perfect fix for the KV cache problem. But there's a catch. And this, right here, is where the obvious solution starts to fall apart. It turns out that the way we've been doing quantization comes with its own hidden costs, a kind of memory tax that actually undermines the very savings it's supposed to create. The dilemma is actually pretty simple. On paper, you promise to make the data 6 times smaller, but in reality, what you get is your 6 times smaller data, plus a whole bunch of extra data that you need just to decompress it. It's like ordering a flat-pack bookshelf to save on shipping space, only to find out the instruction manual is as heavy as the bookshelf itself. Kind of defeats the purpose, right? So what is this overhead? What is this heavy instruction manual? Well, it comes from storing something called normalization constants. Think of them as the instructions for how to unshrink the data back to its original form. For every little chunk of data you compress, you have to store a separate set of instructions on how to scale it back up accurately. And this little tax can add 1 to 2 extra bits for every single number, just eating away at your compression savings. This is the hidden flaw that's been holding quantization back until now. All right, so enter our hero, TurboQuant. Researchers at Google realized that the problem wasn't the compression itself, it was this pesky overhead. So they went back to the drawing board and developed a completely new 2-step approach that was designed from the ground up to be totally overhead-free. And here's how they do it. It's so clever. Step 1 is called PolarQuant. So instead of storing data with standard coordinates, like go 3 miles east, then 4 miles north, it converts them to polar coordinates, something more like go 5 miles at a 37-degree angle. This little geometric trick creates a really predictable structure that completely eliminates the need for those normalization constants. Then, in step 2, this clever 1-bit error checker called QJL comes in and just cleans up any tiny little inaccuracies left over, making sure the final result is absolutely pristine. And the result is a total game changer. By getting rid of the overhead, TurboQuant can dedicate its entire compression budget to what actually matters, capturing the true meaning of the original data. No wasted bits, no hidden costs, just pure, clean, efficient compression.
Okay, so that all sounds fantastic in theory, right? But what does this elegant solution actually achieve in the real world? Well, the results are, and I'm not exaggerating, pretty stunning. First up, a 6-fold reduction in the size of the KV cache. Just let that sink in for a second. The single biggest memory hog in AI just shrunk down to a fraction of its original size. Second, and honestly this might be the most mind-blowing part, it does all of this with zero measurable loss in accuracy. The AI's performance is identical. It is the holy grail of compression. You get all of the savings with none of the sacrifice. It's basically lossless. And finally, all this efficiency translates into pure speed. Because there's so much less data to move around, everything just gets faster. On those powerful NVIDIA H100 GPUs, that means up to an 8-times speedup in the core computation. So let's just recap. 6 times less memory, the exact same accuracy, and up to 8 times faster. Wow. Now, let's put that into context. How does this stack up against what was out there before? Well, compared to doing nothing, the benefits are obvious. But the real story here is how it compares to KIVI, which was the previous state-of-the-art method. TurboQuant delivers more than double the memory reduction with even better accuracy. And just like KIVI, it doesn't require any expensive retraining of the AI model. It just works right out of the box. So, okay, a cool compression algorithm, why should you actually care? Well, because it makes powerful AI way more accessible and economical for literally everyone. It means we can have longer, more coherent conversations. It means AI can run on a much wider range of hardware, which could unlock powerful features right on our phones and laptops, not just in some giant data center. It's fueling this efficiency race, and that could end up being even more important than the race for just building bigger and bigger models. All right, thanks for sticking with me on this deep dive. If there's one big thing to take away from all this, it's that the future of AI isn't just about building bigger, more power-hungry models. It's about breakthroughs just like TurboQuant, smarter algorithms that let us do more with less. And that efficiency is really what's going to bring the power of AI to everyone.